so coming back, we know that quantum computer, that is a term that we've been hearing frequently nowadays. So speaking about quantum computing and quantum communication, how does your work in adaptive quantum optics differ from these quantum other aspects of this quantum physics?
Okay, so my work, well, it is towards building a quantum future for sure. So one way I can say that is different in terms of what it is there already is basically when we are talking about incorporating the encryption method, what right now exists are like software-based encryption. Okay, so basically when you are trying to send in whatever, like even in WhatsApp, even like this message that we are trying to send in, these are all like software-based encryption that is going on online. What we propose in order to do the secure authentication, wherein, it should be like I am actually trying to talk to you, Thalseema. I'm not Thalseema, not somebody else. But how do I know that? So to that end, what we do is we are making a chip through which if we transmit light and the light would be basically be able to be reconstructed the way we want only by that chip. If somebody tries to make a chip exactly like that, they won't be able to do that. Why? Because of the fact that the chip is so small and the designs that we make in them are so small that it is fabrication limitation in itself. So when we fabricate it, you would never be able to fabricate two identical chips. So to that end, that is one of the ways in which we can always ensure that the person we are sending in is unique. And it is actually the same thing which are also used in your like regular every digital devices that you have, which do have a microprocessor in them. They are known as their unique fingerprints. They have their unique fingerprints because of the fact that the chip have these differences in that nanoscopic scale, because of which no two processors fingerprint would be the same. But what we are doing, we are basically now be transmitting light through it in order to say encode a message, so on and so forth.
So that is what adaptive quantum optics does. And like quantum computing is something a bit different from that. Okay.
Adaptive quantum optics has quantum computing as well.
Okay.
The other thing is quantum security. Okay, given that you have
Okay.
a quantum computer, you would need quantum security. Okay, so these are like the
Right.
two aspects that are being dealt with. Okay, so
Right.
quantum computers are used to say like, solve problems or whatever, but also you need a quantum channel in order to do the communication
Mm.
between like, two
Mm-hmm.
parties or whatever. So in order to establish that that channel is secure, you need some encryption method, and that's where we
Okay.
come in. We have to ensure that yes, the two parties who are trying to connect with each other are indeed the two parties, and it's
Mhm.
not a
Mhm.
eavesdrop which is trying to steal data or whatever. And to that end, we are utilizing hardware keys which are like these chips in order to realize this and establish this communication channel. Okay.
Right. Okay.
Yes.
That is really cool. As an experimental physicist, you're not just working on theory, you are also building and testing a lot of things. So, what does a typical day in your lab or in your lab life look like? And what is the most significant experimental challenge that you have faced till now? And how like, have you overcome that?
Okay, thank you for the question. So, before this, I used to work, I used to work in an optics lab, but there I used to basically work in systems which were, they had like these huge lenses and mirrors, and in which I had to like put in laser light and all. And now my system has reduced to chips. So to that, and I'm just gonna share my screen with you. Just a minute. Let me see. Okay. Let Okay, so this is a microscope. You can see there's a chip in there, and let me just pause it there so that you can see yeah. So you see this? So this is my system now. So basically now instead of like the live, really huge mirrors and optics that we use, and like the resonators and stuff, everything. Now everything is on chip, and I want to basically shine my laser light into this chip and try to see, how the light is traversing and how what the transmission looks like and all. So how does that look like? So I have is the same thing over here. Yeah. So this is the same chip that I showed you using like through the microscope, so you were able to see the structures upon that. And here are the fiber arrays that are shining red. And you're basically we are coupling the light, and I think you are able to see some coupling through the chip. I don't know whether you can see my arrow or not, but on chip you can see like some illuminating points. And then the other end of the chip right now, there should be another fiber array connected to that, through which we take the transmission out. So let me see, I think this is also a good one, in which you can see the light coupling through the chip and then going to the other end. And this is, well, yeah. So my typical day in lab is basically to be able to, place the chip nicely onto the stage and do the alignment, do the beam alignment as well, in order to ensure that the maximum light is coupling into the chip and we are not getting any losses. Then basically looking into the transmission, and then categorizing whether the chip is working well the way it should. That is like one method. But this, along with this, I also try to design chips, because according to what I want, what the purpose it should be served. So my particular thing is to now make these chips active, as in these chips that you see are passive chip. What does that mean? That means once the structure is done, that is it. My thing right now is to like place heaters on them, so that we can heat up the chip and be able to change the path lengths of the waveguides within. So this is a typical like resonator system array that you see over here. And yeah, I mean, these are the systems that I work with, in which I try to basically shine light and try to get the output, and then utilize the output in the said quantum communication and this quantum encryption and security. So the good part, and actually the fun part about this chip, as I'm not sure, but you can see like the top half and the bottom half are exactly the same. So what we are, as I mentioned earlier, is the fact that these chips have been fabricated on a single wafer, the same wafer with the same design and everything. But when we look at the transmission of each of these ends, they are going to be different. So that is what we're trying to basically prove here, is the fact that they are unclonable. Even if you design the exactly same structure, still the transmission would be not the same, because of the fabrication variation that comes with it. So yeah. So this is,
That's
yeah, I'm just gonna stop
yeah,
sharing now. Yeah.
that looks like a very pretty maze. Who would know that it's actually a chip? Nice.
Yeah. Yes.
That also looks like it can be very challenging to achieve that feat. So,
I mean, yes, the feet, I mean, chip-wise, well, at least like we do the designing of it, but actual manufacturing and all, again, it's also done within the UT, because the UT has its own like chip making platform and everything as well. And that is a challenge in itself, basically, because in order for us to isolate the electronic component, because it's an integrated chip, right? Integrated photonics. Right now we are not in the pure photonics regime. We still have the electronic and photonic parts interplaying with each other. That's why when I say, like, I want to incorporate heaters, but in order to operate the heaters, I'll need electronics. I'll need a driver, a signal, in order to like do so. So that is one thing. But yeah, I absolutely love the fact, like, the system size is so much reduced, and it's fun to be able to now be able to like control the light and actually utilize it for a purpose which definitely serves for in the like future as